My name is Olafur Jonasson, and I'm going to present my poster, Improvements to NOAA VIIRS SST products produced using the Advanced ClearSky Processor for Ocean, or ACSPO, version 3.0. So I'll start with some background. So NOAA provides satellite-derived SST from VIIRS sensors flown on board the NPP, NOAA 20 and NOAA 21 satellites using ACSPO enterprise system. So the primary product are subskin SST, and then there's the depth SST, which you obtain by taking subskin SST and subtracting SCS bias. So we report thermal fronts, so that's both location and intensity. So ACSPO-based products are reported in native swath resolution as LTP and L3U 0.02 degree equiangular projection. So SST from all VIIRS sensors are combined in the super-collated SST product from low Earth orbiting satellites. So that's ACSPO L3S LEO. And the ACSPO team finished development of ACSPO 3.0 earlier this year, and operational production is expected to start in early 2026. So updates in version 3.0 are the subject of this poster. So they include a redesigned ACSPO ClearSky mask with the main aim of reducing overscreening in dynamic SST regions, such as the Gulf Stream. And SST retrieval coefficients have been retrained to mitigate systematic downward drift of VIIRS datum SST and to improve retrieval sensitivity of the depth SST to be comparable to that of subskin SST and close to 1. ACSPO file metadata was updated to comply with the GTS version 2.1 standard, so previously was 2.0. And the RDAC in ACSPO file name is now a NOAA for all ACSPO products, so it was previously either STAR or OSPO, depending on where the data was produced. And in this book, we're going to provide an overview of the updates in version 3.0 that are relevant to users for ACSPO VIIRS and the downstream L3S LEO products. So the main update was the redesigned ACSPO ClearSky mask. So the purpose of ACSPO is to, the ClearSky mask is to identify clear pixels for which SST can be accurately retrieved. So the most common reason for a pixel to be flagged as not clear is obstruction by clouds. So that's why it's often referred to as the cloud mask. Other reasons include abnormal atmospheric conditions not represented in the SST algorithm training dataset, and sensor issues and atmospheric aerosol. So in ACSPO version 3.0, the mask was redesigned with the goal of reducing reliance on agreement between satellite-derived SST and lower resolution first-guess SST from level 4 SST products. So figure 1 shows a comparison of the super-collated VIIRS SST product, so as L3S LEO PM. So this is imagery produced using version 2.8, so it's the top panel, and version 3.0, and it's the bottom panel. So the purple rectangles emphasize the regions where high resolution cold SST features were often misclassified as cloud in version 2.8. But if you look at the lower panel, they are more correctly classified as clear in version 3.0. So that's because we reduced the reliance on the mask on the agreement between satellite and level 4 SST. So the improvements in the ACSPO ClearSky mask demonstrated in figure 1 were accomplished via redesign of the mask, which included revisions of existing cloud tests, as well as a suite of new reflectance, spectral, and texture-based cloud tests that are described in the ACSPO algorithm theoretical base document, or ATBD. So new additions to the ACSPO ClearSky mask include the long-wave infrared test, which is a nighttime-only test where the cloud predictor is the difference between SST retrieved using the daytime SST algorithm. So it's using VIIRS bands centered near 8.6, 11, and 12 microns. This difference between that and the nighttime algorithm, which in addition to these 3 bands, also uses the VIIRS mid-wave IR band centered at 3.7 microns. Figure 2 shows the examples in a scene where the long-wave infrared test can identify near-surface clouds that are often challenging to differentiate from neighboring clear pixels based on the difference between retrieved and first-guess SST alone. So the top left panel shows all sky imagery, so the SST imagery. So this is with no cloud mask applied to it, and it's also showing the satellite minus level 4 SST. So we can see here, and all around there are real SST features. So those show up because the reference is level 4, and you can show these are real SST high resolution features. And you can see here that regions emphasized by rectangles. So these are clouds. So these clouds can be difficult to identify just based on the retrieved SST alone, because you see they're similar in retrieved SST similar as for the neighboring SST features. But if you look at the same imagery, but the difference between the two the daytime and the nighttime STS algorithm, you can see that the clouds, this type of cloud, they pop out much more. And you can see that the real SST features surrounding, so they are mostly gone because the two ST and algorithms agree with those features, so the difference is small. So the lower left feature shows the retrieved the SST minus level 4 ST with the cloud mask applied in gray. So this is the mask without the long wave infrared test. You can see there are some remaining cloud leakages. You can see this in both rectangles. And in the lower right panel, you can see the same but now you included the long wave infrared test. You can see that it's much more efficiently screens out these cloud leakages. So this reduced reliance on first guess SST in the ACSPO version 3.0 mask resulted in significant improvement in the clear sky ratio. So that's the fraction of clear sky ice ocean pixels. So this is without degrading validation statistics against in situ SST in terms of mean bias, standard deviation, and robust standard deviation. And this is demonstrated in figure 3. So the rectangles, the figure 3 shows the top panel shows histograms of mean bias against in situ SST from drifters and tropical moorings. And then the bottom panel shows the corresponding nighttime results, and the left panels are the 2.8, and the right panels are the 3.0. And you can, for example, if you just look at the daytime results, so you can see a rectangle here says that the clear sky ratio is 19.84% with 2.8, and now it's up to 21.27 in version 3.0. And this is a whole year. This is based on a whole year of data, 2023. So you get similar improvement for the nighttime ST. So the clear sky ratio is 18.7% for 2.8 and up to 19.87 for 3.0. And in another major change between 3.0 and 2.8 is the positive 0.13 Kelvin jump in daytime ST. So this is highlighted by the lower rectangles in figure 3. So if you compare the mean bias here, the mean bias in 2.8, that's negative 0.13. And then version 3.0 is close to 0. So this is based on recalculating the SST lookup or retrieval coefficients to correct for long-term drift in VIIRS calibration. So as for future work, so we plan on performing full mission reprocessing of ACSPO VIIRS SST for MVP, NOAA 20, NOAA 21, and provide users with a consistent and stable time series for ACSPO version 3.0 VIIRS SST. Thank you.